Welcome to Tolofsen Physics. So what we're going to talk about today is how to draw a Lewis dot structure for a covalently bound molecule. So what are covalently bound molecules? Well, when we looked at ionic compounds, what we saw were a metal and a nonmetal that completely transfers an electron from one element to another. Well, when we're talking about covalent bonds, what we're basically doing now is we're not transferring an electron from one atom to another. They're going to be shared in a tug of war, and that tug of war is going to be won by the atom that has what's called the most electronegativity, which we'll address at another time. And so basically this electron, what we're going to do is we're still going to try to fill the outer shell of electrons. But in a covalent bond, that electron is going to exist between two elements. So let's look at our most familiar example. So water, we all know, is H2O. And so H2O, when we look at the periodic table, hydrogen has one valence electron, so I'll draw it that way. Oxygen has 6. Now the way that I draw valence electrons is I always go top, bottom, right, left for my first 4, and then I can pair up number 5 and number 6. So that leaves me, and I'm going to kind of draw this, I don't usually draw this, but holes here and here that needs to be filled. And so since those need to be filled, they're going to be filled by the hydrogen atom. And so now you can start to see, why is there 2 hydrogen atoms paired up with an oxygen? Well, this one's going to get shared and fill one of these spots, and this a second one, so let's draw a second one because I got 2, is going to get shared there. So how do I draw what's called the Lewis dot structure for that? Well, I have oxygen, and let me just put in what I had before, and now I'm going to bring a hydrogen in here. And I'm actually going to use an X for the hydrogen just to show that it came from somewhere else. I don't have to do that. I could leave it as a dot. And then here's my other hydrogen. And so why is this energetically favorable? Well, I'm going to actually draw this circle. You don't have to draw this either. But how many electrons are in the outer shell around the oxygen now? So there are 8. That's the goal. We want 8. Now, what about hydrogen? So hydrogen's this, and hydrogen is this. So each hydrogen has 2 electrons. And if we go back to the periodic table, well, the top of the periodic table, you can only fit 2 electrons, right? Hydrogen, helium, that's 2, that's it. And so when we go back to here, we have now filled each outer shell of electrons so that it works. All right, so let's take a look at another combination. So how about oxygen gas, O2? All right, so when you look at the periodic table, we already know this, right? There are 6, 1, 2, 3, 4, 5, 6. And then I'll have a second, 1, 2, 3, 4, 5, 6. All right, so now what happens? I have a hole here, hole here, hole here, hole here. I got 2 holes in each one to fill. So how am I going to do that? Well, basically what I can do is I can share more than one pair of electrons. And what that's going to do is it's going to form, in this case, a double bond. So what do I mean by that? So if I take this oxygen and I'm going to draw 1, 2, 3, 4. Those are these 4 by itself. And I'm going to put those other 2 here. And I'm putting them there because I'm going to draw this other oxygen. Let me use a different color for the other oxygen because then you can see where the electrons come from a little easier. So 1, 2, 3, 4, 5, 6. So this right here is what I mean by double bond. I now have 4 electrons that are shared between those. And so does this meet my requirement of having a full valence shell of electrons? And let's find out. So what are all the electrons that are around this left-handed oxygen? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. Cool. That's a full outer shell of electrons. And then the same is going to be true, since it's a symmetrical molecule, of the other oxygen. And so I can share more than one pair of electrons. I'm always sharing pairs of electrons, no matter what. In this case, I'm sharing 2 pairs of electrons to make it work. All right, let's look at one more molecule. So let's go with the simplest organic molecule I can think of. It's called methane. So this is methane. All right, so methane is CH4. And so CH4, we already know that hydrogen is just got 1 dot on it. What about carbon? Well, carbon is in column 14, which means it has 1, 2, 3, 4 valence electrons. So to fill those 4, well, I'm going to take 4 of these, and it's going to work, right? So let me switch to a different color for hydrogen. So hydrogen, I got 1 there. So now I got 5 around carbon. Let's put 1 down here. Now I got 6 around carbon. Let's put 1 over here. Now I got 7 around carbon. And then finally, it's CH4. I'm going to put 1 more up there. I got 8 around carbon. Right? And so hydrogen can only make single bonds because it only has the ability to have 2 electrons in its outer shell. And so it's going to connect everywhere. This is part of the reason why carbon is the building block of life, is because it has such versatility in being able to bond with other atoms. All right, so you try one thing, and I want you to try pH 3. So pause the video and do that real quick. All right, so phosphorus has 1, 2, 3, 4, 5. And so the hydrogens will go 1 there, 1 there, and 1 there. And then all our requirements are met. All right, so keep practicing this, and good luck.